All right. Hello. Hello and welcome. So, let me make sure everything's set up right here. You can see me in the corner. This is my little studio here. Hello, hello, hello. Just making sure this all works. I'm recording. All right, perfect. Hey guys, welcome to our next video. All right, on continuity. That's our next lesson. It's 1.8, chapter 1.8. We just finished up doing stuff with limits, which we're still continuing right now with continuity. We learned the squeeze theorem. That was our first kind of official theorem in calculus, and now we're moving on to a second kind of theorem in calculus, and that's dealing with continuity, which kind of builds on that idea of limits. So we talked about in the past, like what a limit is and how a limit approaches a certain value, and we talked about different cases that can happen with like holes and asymptotes and stuff. And now we're going to kind of discuss the reverse of that almost using limits, and that's talking about continuity. So proving like how to prove that we are continuous at a point or on an interval. And so it's kind of the other way around of looking at things, not holes or asymptotes, but continuity. And we're going to talk about how limits are used to describe that. So I'm going to try to keep it under 30 minutes if I can. That's my goal. And if I get to 30 minutes, I'm going to try to cut it short and finish the rest in class. But you got a warm up here, and the warm up is practicing. Practicing doing limits, stuff that we've seen before, so I'll let you do that on your own. This one right here, use a calculator. So if you want to do this one, use a calculator. That's the only way we know to do that one right now, and that's actually a specific type of limit we're going to learn how to take in the future using actual calculus. Right now, there's really no way to simplify that, but just to look at a calculator. Okay. All right, so try the warm up. Now let's talk about continuity. So a few ideas here. It says that a function is continuous at a if, and it's a pretty basic idea. We're continuous at a if the limit at a from approach from both sides, so the left and right limit, is equal to the value at a. So that means that the lines from left and right are going to meet at the same point, and it's going to be defined there, which literally makes a defined function. Okay. Now, in order to get to this point, it requires a couple things. So in order to define continuity, we have to prove three things. And the third thing is pretty much this, the summary. Okay. In order to do that, we first have to figure out f of a. We have to just show that f of a is in the domain. It's defined, meaning that I can plug a into the equation and actually get out a number, that there's no asymptote or holes, or that there's no undefined point. Okay. And then we have to show that the limit exists. So we showed this piece of it. The second step is to show this piece of it. Okay. And then once I show each of those pieces are equal, once I find each of those values, then I can just finally make that conclusive statement that they're equal to each other. Okay. Now, like I said, in order to do this, to find these three requirements, the steps are those three requirements, and I'll just write them out. Step one is to literally do f of a. I have to figure out what f of a equals. It's going to equal some, I put c for constant, some number. Okay. Now, in order to do number two here, in order to find the limit, well, we discussed how to prove a limit exists, and that's to show that the left and right limit are the same. So we kind of have to break this up into to a couple parts here. We have to say the limit as x is approaching a from the right, okay, of f of x, and I have to find the limit as x is approaching a from the left of f of x. Now, if I can find those two values, all right, and show that they both equal the same number, all right, then I can make the general assessment that the limit as x is approaching just the generic a of f of x equals c. Okay, so in order to figure out two, again, you have to show the left and right are the same. Now, then, if what you found in one matches up with what you found in two, then the conclusive statement to prove continuity, you can finally just state, well, it's continuous because the limit as x approaches a of f of x, so what I found in number two is equal to what I found in number three. Okay, and what that looks like, so like right here on my graph, here's a, like here's the point a. What has to happen is pretty much I need to be able to draw the graph without lifting my pencil. So I need to be doing something like this. Okay, so you see right here at the value a, we got f of a is defined, and we got that the left limit and the right limit are all meeting there. So you can obviously see that that is a continuous point. So if we can show these things here, all right, if I ask you to prove that we're continuous at some value a, that's how we do it. All right. Which isn't too bad. We're going to do some examples of it. Now, I almost want to skip over this slide, but I'm not gonna. It's stuff that we kind of already know, but just again to show you examples of kind of going through those steps, okay, with a graph here, kind of looking at each of those steps, and how like once we reach a contradiction, we can just kind of stop. So I meant to take these parts of this off. I didn't mean to copy that on there. I'm sorry. But like, look at an example here, like p of x, for instance. Okay. So like, I'm just going to kind of show you like how the process works in your steps. Okay, so if you kind of meet a contradiction, you can stop. Like for instance, right here. So if I follow those steps, I can say, okay, number one, let's figure out what f of a is. Okay. Well, if you look right here at a, there's a hole here and an asymptote here. There's no defined point for a, so I'm going to say does not exist. Okay, so therefore, it's not continuous. It is not continuous at A because the step one of the criteria doesn't happen. Now you can show the rest if you really want to. Like you can say the limit from the left equals infinity, the limit from the right equals some other number, I don't know, and that means that the limit is also non-existent. So, but honestly, if you just go down the steps and the first contradiction you come across, you can just stop there because there's really no point in going on. Like okay, again, for instance, on this one. If I did step one, you can say f of a equals, well again, there is no defined point. They're both open circles, so you can say does not exist. So again, at step one, does not exist, so it's not continuous. I mean, you can discuss that the left and right limits aren't equal as well, but I mean, you can obviously tell it's not continuous. Now for number three, if I'm trying to describe it, I can say step one, f of a. Now in this case, f of a does equal a number. It is defined. It's defined right here at the closed circle C. Okay, so we can't just stop there and say it's not continuous. Okay, we know it is by the graph, but to prove it, we have to show a couple steps. So let's do the next part. Let's talk about the limit as x is approaching a from the right and from the left. All right, from the right it equals b. From the left it equals c. So you can see that those do not equal each other. All right, so therefore the limit, or the generic limit here from left and right, does not exist. Okay, so step two is where we would cut that one off. It's not continuous. Number four, you can probably just kind of jump ahead here, like jump to step two. You can see that the limit does exist. The left and right limit both approach b. So step two is actually a check. But at the very beginning here, if I did step one and said f of a equals, again, there's no defined point there. So we would just say does not exist. So we can stop right there. If it's not defined at the point, there's no sense in going on to number two. All right. All right, number five. I'm going to try to squeeze it in here. The f of a, all right, step one, does exist. It equals b. All right. Now, I'm not going to write it down for sake of space here, but if I were to go on, so that's a check. If I were to go on to step two, I guess I can squeeze it in here, and show the left and right limit, all right. All right, actually, this is probably a good thing to write out. Okay, I'm going to say the limit as x is approaching a from the right is actually equal of f of x is actually equal to the limit as x approaches, come on please, dadgummit, as x approaches a from the left. Okay, well, anyway, the left and right limit are equal to c. So actually step two checks off. Okay, we got that the limit exists, it equals c, and we got f of a equals b, but the part that doesn't work is actually step three. All right, the step three, does the value equal the limit? In this case, f of a does not equal does not equal the limit. 1 equals b and 1 equals c. So that's an example where you can go through the first two steps just fine, but then the third step is the one that proves that it's discontinuous. The limit as x approaches a equals c. So that doesn't work. Lastly, number 6 of all of them is the one that follows the criteria. You can even see it's a nice continuous line here. It proves everything. F of a equals b, and I'm going to just skip down and just say, I'm just going to go ahead and say the conclusive statement here, that f of a equals the limit x approaches a of f of x, and they both equal b. So that's the statement we're trying to get to. We can check that bad boy off. All right, not too bad. So maybe pause the video, look through those, and kind of reason through the graphs. But that's just kind of an example of looking at some graphs with continuity. All right, let's discuss this next one. Okay, it says now it's no longer a graph; it's an equation. It's a piecewise equation, which happens to be a very common question that we ask about continuity. It says, is the following function continuous? Justify your answer. Now, it didn't specify at any point, so it means the whole function. So obviously we can tell the point that we're interested in is going to be 2, okay, because that's where the break in the graph is at. I want to know what's happening at that break. I want to know if it looks like any of these functions from before. If there's holes or jump discontinuities or anything like that. Okay. So we got to figure that out. Now, it is talking about the whole function, so we are curious about what's going on maybe to the left of the break and to the right of the break. So we're going to talk more about this later, but you can maybe make an observation that this is a cubic and this is a linear. All right, both of them are polynomials. So maybe we can just make a little note here at the beginning because this is going to help us later. We're going to make a note that polynomials are continuous. And this right here means for all of x. So polynomials are continuous for all of x. So I got that part taken care of. Now the part that I'm really curious about is the continuity at that specific point. Now we have a way to do that, okay? We have steps. So let's start off with our step 1. Okay. Step 1 we're curious about is f of a, or in this case f of 2, is it defined? Okay. Well, if you notice in the two functions, we do have 2 being included in the domain. All right. So I would plug it into this function right here. So this is equal to negative 2 times 2 plus 9, which in this case is 5. So f of a exists. F of a equals 2, or I'm sorry, f of a equals 5. So that part is a check. Okay. Now let's move on to step 2. Step 2 is to discuss the limits, right? So we want to see what the left limit is, what the right limit is, and see if they match. And that will conclude step 2, and we can keep moving. So I'm going to start with, I'm going to do the limit first of all, as x is approaching 2 from the left, and we'll also do the limit as x is approaching 2 from the right of f of x. Okay. Now, since we're talking about a piecewise function, right here at 2, okay, that's the break in the graph. We have some graph going on the left side and some graph going on the right side, okay? So the graph that's coming from the left side, that's the one that I'm talking about with the left limit. And the graph on the right side of 2, so anything greater than 2, that's my right limit equation. Okay, so we got 2 different graphs on either side of the break. So if I were to say the limit as x is approaching 2 from the left, I'm going to use the function that's dealing with the values less than or equal to 2, which in this case is the linear function. All right, so 2 from the left would be me doing negative 2 times 2 plus 9, which equals 5. We already showed that. And then 2 from the right, so that's using the values of the functions over here. So where x is greater than 2, I'm going to do it in that cubic, which is 2 cubed minus 2 times 2 plus 1, which in this case is 8 minus 4 plus 1, so 5. And what do you know? They're equal to each other. Okay, so we can say the generic limit exists. We can say that the limit as x is just approaching 2 of f of x is going to equal 5. Now, so we showed step 1, we showed step 2, we showed both of those exist. Now the observation that we make is that those two values are the same. So then in step 3, we can make that conclusive statement that defines continuity at a point. So we can say the limit of as x approaches 2 of f of x is equal to f of 2, which in this case is equal to 5. That's the statement that we've been trying to get to. Okay. So we showed the break in the graph is continuous. We talked about the intervals on each other side are also continuous for all of x because they're polynomials. So that's about it in a nutshell. So f of x is continuous. Cool. Now if it had specified continuous, say, at x equals 2 in the problem, then we wouldn't have to discuss this piece of it. But because it's talking about the whole function, it's probably a helpful idea to go ahead and do that. All right, let's move on, shall we? All right, so like we said, continuity at a point is the left and right limits got to match up. We talked about the criteria just now. Now, I could also kind of narrow down my criteria here. I can say that a function is continuous from the right, all right, if the right limit equals the value. So that would be this graph right here. So let's say that this is a right here. And it's continuous from the right is if the right value, that's ugly, but the right value equals that. A function is continuous from the left if the left limit equals the value. So that would look like this. Here's a, here's us coming from the left. Okay. So I've seen questions in the past where they'll give you, say, like an example. Let's do this example. I'll stick with the example right here. They'll give you this graph right here. And they'll ask, like, is it continuous at A? And you might say no. And they'll say, is it continuous from the left? Is it continuous from the right? So in this example here, it's only continuous from the left at f equals A, at x equals A, because the left limit matches up with the value. So it can sometimes specify that at a break in the graph. Not always, but I did want to discuss that. Most of the time, it's talking about like a generic continuity at point A, and not just from the left to right. Again, wanted you to know that. All right. Next, it says if f and g are continuous at A and c is just some constant, it's defining c as a constant to make the next statements true, then the following are continuous at A. So all this is saying, this is a helpful thing to kind of keep in your notes here, is it saying is if you know f and g are continuous at A, then adding the functions together will also be continuous. Subtracting the functions will also be continuous. Taking function f or function g, so or c times g, and just multiplying by a constant, it's still going to be continuous. Multiplying the two functions together makes it continuous still. And even if I divide the functions where g of a is not equal to 0, it's still going to be continuous. So doing all these different operations with the functions is not going to change the continuity of it, especially if they're already continuous at each function, right? I mean, for example, I could say that f is equal to x squared and g is equal to x cubed plus 1. Both of those are polynomial and both of those are continuous everywhere. Think about all those operations as I talked about. Multiplying them, subtracting them, multiplying them by a constant, dividing them. If I do any of those operations, they're still going to be continuous at some value a, okay, if they're already continuous there. So anyhow, just keep that in mind. And this right here is kind of talking about that last piece of the graph, talking about kind of over an interval here. This is just important when talking about more than just one point. Okay, talking about an interval, we're talking about trying to find a continuity on a domain. It says a polynomial is continuous everywhere. A rational is continuous everywhere it's defined. Okay, so And root and trig functions are also continuous everywhere they're defined. I know that's an obvious statement, but these are three statements that you are allowed to use. Okay, so like in the last example, I made the connection that a polynomial is continuous everywhere. When I say a rational is continuous everywhere it is defined, I'm just saying like if you can take the like a rational and put it into a function like any value, if it's defined, then it's continuous there. Okay, so it's everywhere but what makes the denominator 0. It's continuous everywhere else. Same thing with root and trig functions. Like for example, if I take the square root of x, that's going to be continuous for all values greater than or equal to 0. So it's continuous everywhere it's defined, which in this example would be the interval 0 to infinity. Okay. All right. Let's show an example 1 here, of kind of using these ideas up here and how extremely helpful they are. Okay, in discussing where the following is continuous. This is really helpful. Okay, look at this. It looks like a whole mess of things, and it wants to know where the following is continuous. And it's a lot. Okay. Well, it turns out, kind of based off of more specifically like number 1 here, if I have in this case 3 functions being added and subtracted together, if I can figure out where each of them are continuous, then the whole function is continuous with all the numbers they have in common. Okay, pretty much because of this idea here. If I can find the shared continuity, all right, then that's where the entire function is continuous. So let's look at these each as we let's break down each of these. Okay, so just kind of, we know what a square root function looks like. I actually already drew it right here on the right. We know that's going to be continuous everywhere it's defined, which in this case is 0 to infinity. Okay, I just discussed that right here. Okay. In this next piece right here, okay, x plus 1, x minus 1, that's a rational. It is continuous everywhere it is defined, and it's defined everywhere but at x equals 1. We have a vertical asymptote at, x equals 1. Okay, so that means that it's defined everywhere but there. So in this case, that is negative infinity all the way up to 1 and 1 to infinity. Okay, so that's the interval on which it is continuous. And then the domain finally for the last one here, x plus 1 over x squared plus 1, is a rational. So we got to talk about anywhere that it's defined. And the only place that it's not going to be defined is what makes the bottom 0. So let's let the bottom equal to 0. Now if I do that, x squared equals negative 1. And I can't take the square root of a negative number. X equals the square root of negative 1. I mean, I guess technically that's equal to the imaginary I, but that's not an actual value. So there is no values of x that makes this undefined. So it's defined everywhere. So in this case, the continuous interval is negative infinity to positive infinity. So the thing is, like, we're able to find the domain of each of those 3 pieces just from previous math courses. And it turns out that the shared intervals are where these functions are going to be, as a whole, continuous. So I like to draw this on the number line here. I like to draw that continuity on like a legit number line. Okay, so here's my number line. Okay, so for the first one, like for square root of x, it is defined from 0 to infinity. So I'm going to draw that on my number line. That's 0 to infinity. Okay. Now, the next piece, the middle piece, is defined from negative infinity to 1 and from 1 to infinity. So if this is 0, I'm going to put 1 right here. I'll do this in red. It's defined from negative infinity all the way up to 1, and then from 1 to infinity. So that's where the middle piece is defined as continuous. And then lastly, I'll do this one in blue. The last one is continuous everywhere. Okay. So where do these 3 continuities overlap? All right. Well, if you can circle like a vertical, piece of it that overlaps, then that's where it's all continuous. And I'm seeing that right here and right here. So if I want to know where this entire thing is continuous, it's actually going to be from 0 to 1, and it doesn't look like it includes 1 because the middle graph doesn't include that. But all three of them do include 0, as well as from 1, non-inclusive, all the way to infinity. So this is where, and actually I just realized that I think my camera is actually covering all that up now that I think about it. So what I'm going to do is I'm going to try to pull this up, scroll this so you can see it. I apologize. I just realized that. So let me figure out how to do that. I want y'all to be able to see that. I'm sorry. Did I do that in the last examples? I don't think I did in the last examples. I might have done it in this example. I think my graph covered that one as well. I just realized that. I'm sorry. I've made that mistake before. I don't think that one. Okay. Well, if it did, dadgummit, there's got to be some way that I can extend. What if I do this right here? Let's go down. I want y'all to be able to see that. I'll do this. Dang it. Oh well. Okay, well anyway, I'm gonna select this and maybe we can oh crap. Maybe I can move all this. I'm gonna try to move all this so you can see it real fast. Dadgummit. Ah. Okay. Ha. I moved it over here a little bit to the right, to the left so you can see it. But okay, in case you couldn't see it because of my picture there, again, I just drew a number line with the domains of each of the three pieces of the graph, and I showed that where the overlap was is where it's continuous. So I circled the continuity, and you can check it in the calculator if you want to graph that entire function, but it's over this interval in which it's continuous. Okay. All right. Well, I'm running out of time here. I'm about 5 minutes away. The last thing I kind of want to talk about is a theorem that has to do with continuity. So far, all we learned how to do is define continuity. We learned how to talk about continuity at a point and over an interval. The last thing I want to talk about is, I guess, the second theorem in this class. And actually, I think this is the most, this is actually one you might see on the final exam. Squeeze theory was great. I don't think they usually put squeeze theorem on the AP exam, but you'll more than likely see an intermediate value theorem on there as well. And I think it's a very straightforward statement. Okay, and this graph is used to kind of explain it. It says if f is some continuous function on the interval a to b. Okay, so here's a, here's b. We've done some tests. We've already showed that it's continuous on the interval a to b, or it's known that it's continuous on a to b. And it says that n is a value between f of a and f of b, where f of a does not equal f of b. So another way of saying that is this is f of a. We got some value in f of b. And you can see that clearly on the graph right here. Okay, so what we're going to be given is that the function is continuous and that we have some value between my endpoints. Then there has to exist a number c such that f of c equals n. I think that's a pretty straightforward thing. So let's say we have f of a here. Okay, let's say we have f of b here. All right, and I know that it's continuous between a and b, and I know that some n value is between it. There is no way that I can get, there is no way for me to get from a to b without crossing at some point this n value. It could be closer to a, it could be closer to b, but at some point I'm going to cross this vertical line where C's at, and it's going to be intersecting this horizontal line. We're going to meet at that value. There's got to be some point. Okay, it's just by definition of continuity. I mean, there's no way for me not to pass through f of c equals n. Okay, and I think you can probably see that from the graph, and we can discuss that further. All right, I got a couple minutes left before I reach the 30-minute mark, but well, I guess I can. All right, I'm going to hold off on IVT then. Okay, I'm going to hold off on IVT would be a part of our lesson. That's which is intermediate value theorem. So you at least know what it means. We'll do this in class. It's only got a couple minutes left. It says use IVT to prove there is a root on the interval 1 to 2 for the equation x to the 4th plus x minus 3. Again, I guess it's probably best we do that in class together, where you can ask questions. So as long as you know continuity so far, you're doing all right. All right. Well, that about does it. I'm at 30 minutes and 48 seconds. I got to stop. All right, y'all have a good day. We'll see you in class.